Hello everyone. Today we are going to see vector fields on surfaces. What we have already learned what is mean by vector field, and we have seen tangent space and all such things we have seen already. Once again the notation we will memorize. We were representing the n plus 1 dimension Rn plus 1, and the vector space at a point in Rn plus 1 we will notate as Rpn plus 1, the collection of all vectors originating from P, and the vector field we will notate as x bar, and x bar of P is a vector. Its notation is P comma x of P, and the vector field is defined on a on a open set U in Rn plus 1. This is an domain of x bar. So for all p element of U, you can find a vector in the vector field. So x, this x is a function defined from U to Rn plus 1. So corresponding to each P in U, you will get a vector. That vector will be depending on the function x of P, the point whatever gets, you can draw the vectors at each point. This is the vector field in this domain. Now we are going to discuss the vector field on surfaces. We have learned what is meant by n surface, and n surface S can be written as F inverse of C, and you can tell that del f of p is not equal to 0 if it is regular. All those definitions we have seen, correct? And we can represent the tangent space of this n surface as sp. SP will give you the tangent, collection of all tangent at the point P on the surface S. So SP you can write, and SP perp represents the uh, uh, del F of P perp, right? Del F of P. The color, SP perp is the span of del F of P. Okay, only one vector combination will come in SP perp. So SP will come as del F of P perp on the vice on the opposite. Okay, so whatever. So these much things we have learned already. So now we are going to concentrate x bar, the vector field on n surface. On n surface, as here we were considering any domain U, the domain we are going to replace as our n surface. So the vectors whatever we are going to consider is only that lies on the surface S alone. So the P whatever we are taking is coming from S. So, some two typical type of vector fields on the n surface, you can tell what is that. I'll draw a figure here like a circle. This is an n surface, one surface, right? Uh, Circle, two circle I am drawing here. I'm going to draw a pattern of vectors on the circle. First one I'll draw the tangents. Okay, so tangents at each point of the circle I can draw. This is one type of vector field. Okay, tangents coming as tangent to each point in the, so this is your, the circle is your S. Okay, the circle is your S. If I draw like this, you should not misunderstand, it's like a vector. I'll draw another color. So this is your S. Okay, and the vectors you are notating here, these are your x bar of P. The point, this is one P and this is another P, likewise this is x bar of, so the total you can represent it as x bar. Okay, another vector field I can draw is uh, the perpendicular vectors I can draw, right? Each point I can draw normal vectors. So like this I can draw, this will come like normal to the curve. Okay, these are normal vectors. So this is also like the on the surface, n surface S. This is your n surface, one sphere it is. So this is your S, and these vectors will form another vector field x bar. So this is called tangent vector field, and this is called normal vector field on S. So in short, you can tell if x bar of p is tangent to s, then x bar is called tangent vector field, and if x bar is normal to s, then it's called normal vector field. So typical type of vector fields. It's not necessarily only these two are the vector fields on S. You can have so many different vector fields you can define on S. That doesn't matter. These are two types that only we are mentioning. Some special type. Okay. Now we are going to see a theorem. The theorem says the existence and uniqueness of integral curves on n surface. So use the theorem from the previous chapters. Here theorem that we have to prove is theorem 1, that is let S be an n surface in Rn plus 1 and let X be a smooth tangent vector field on S. So we have a point P from S, then there exists an open interval I containing 0 and a parameterized curve alpha such that alpha of 0 equal to P and alpha dot of T equal to X of alpha of T for all T element of I, and we can find a beta, another parameterized curve such that beta and alpha will coincide in the interval I tilde. That's what we have to prove. So here this looks like some theorems that we have learned already in your previous chapters. I think I have quoted the theorem below. That is, just check the difference between these two theorems here. See, this theorem, in the first theorem we have S and N surface. Here they are not mentioning any N surface, and X be a smooth tangent vector field. Here it is just a smooth vector field only. Here it is smooth tangent vector field on S it is. Here it is on an open set U. Okay, and let P is an element of S, then there exists, and the remaining part is all similar, and we have an extra condition also here to prove. So you will use this theorem definitely to prove this theorem. How to do it? To prove this theorem, you have to use this means you need an open set, right? Then only you can use this theorem. Here we have a n surface S. So first our aim is to construct an open set U that contains S. So that's what first we will do. Once you get an open set U and a smooth vector field X on this U, then you can use this theorem. Okay, so here we will first construct an open set that contains S, and we will construct a vector field on that open set. Okay, so what we will do, first we will find an open set that containing S, and we will construct a vector field that is defined on that open set. So whatever vector field we are constructing should have a connection with this smooth tangent vector field. Then only you can prove this theorem. So these two things we will establish first, then we will use this previous theorem to prove this present theorem. Okay, so let us see how to do it. So first of all, what is given? You have x, it is given that your x bar is smooth tangent vector field. Okay, smooth tangent vector field. I'm writing in short vector field as VF. Okay, so S bar is smooth tangent vector field on your n surface S. Okay, S is an n surface in Rn plus 1. Okay, now let us consider an open set V from Rn plus 1. Okay, this is an open set in Rn plus 1. We have considering such a way that S is completely contained in V. So we are considering an open set V that containing S. Okay, so let it be there. First, that is the first open set we are considering. Now we need to match it with the n surface also, right? So here if you have an open set, you can have a vector field on that also. That is, let x tilde is a vector field on V, defined on V, such that x tilde of Q will be matching with whatever the smooth tangent vector field we have, that will be matching with that for all Q element of S. Okay, so we are considering the smooth vector field x tilde on V in such a way that x tilde and the vector field x will be matching on this S. So that means the restriction of x tilde to S is coming as your x bar. Okay, let it be there. Now I am going to consider, since S is an n surface, you can have a function f from n open set U to R, correct? In such a C element of R such that you can write S as F inverse of C, correct? This is true. And also del F of Q must be del F of Q must be not equal to 0, correct? Del F of Q is not equal to 0 for all Q element of S, correct? Because in the N surface, whatever points that comes in this F inverse of the del F of Q must be not equal to 0. So this Q must be coming inside your U, correct? Because this entire F inverse of C is a part of this U. So this is contained in U. Okay, so S is contained in V and S is contained in U also, correct? So U intersection V, if you take, S will be coming inside that U and V. Why? Because this is a common part of U and V. So if you take intersection, S will also come inside that, correct? So I'm going to define W in such a way that set of all Q element of U intersection V such that del f of q not equal to 0. Why have taken del f of q not equal to 0? Then only you can have all these points that comes on this S. Correct? So from this S, whatever points that comes, that will come in this U intersection V. So this implies that S is coming a part of W. So we have constructed a W in such a way that all the points of Q, we have del f of Q not equal to 0. Okay. So we have come to apply the theorem now. We have constructed a U open set, okay, and a smooth X bar constructed a U now. What is that U? In here we our U is W, okay. Now what you need next part? You need a smooth vector field on that set. So how to construct that smooth vector field, that I will show you. So W already I have written. What is W? Set of all Q's element of U and in the intersection with V, whatever be the set comes from that, we are making such that del f of Q not equal to 0. Since del f of Q not equal to 0 means all the elements of S will come in that. Means S will come contain int W. Okay. Now I'm going to make a vector field for W. Okay. I'm going to define in such a way that, see, I'm defining white bar of Q is equal to x tilde of Q minus x tilde of Q dot del f of Q divided by norm del f of Q, okay, into del f of Q. What is the peculiarity of this vector field? This is a vector field constructed from x tilde. What is x tilde? X tilde is a vector field on V. Okay. So here if you take the dot product with del f of Q, what will happen? Here x tilde of Q dot del f of Q will come minus this whole thing will be here as such. Then del f of Q dot del f of q, okay, dot product will be distributive, okay. So here del f of q dot del f of q will come norm del f of q square. So these two terms will get cancelled. Here it will come divided by, right, a numerator by del f of q will come here. So these two terms will get cancelled. Then you will get x tilde of x tilde dot del f only will come here. It will come norm del f del f square comes. So these two get cancelled, only this comes. These two are one and the same. So this is equal to 0. This is true for all Q element of W. Okay, for all q element of w, here del f of q is not equal to 0 in this domain of w, so this definition is possible for a w. So this such a vector field you can define on w because del f of q is not equal to 0 on w. So here for all q element of w, this is equal to 0. That means this y bar will come like a orthogonal to del f, right? So what I can say, y bar of q must be equal to x bar of q for all q element of s. Why? Here on S, if you take a point, x bar is the tangent vector field we have already told. If it is tangent vector field, dot product with del f of q must be equal to 0. So if it is dot product with equal to 0 means it is same as your y bar on W, correct? So y bar and x bar will come one and the same in S, and S is coming inside your W, correct? So the rules are not violated. All the vector or vectors from your defined on your w is coming dot product with del will come equal to 0. That implies these are coinciding in S. Okay, so y bar restricted to S will give you your x bar the same. So we have all done what we have done. We have defined an open set W, and we have defined a smooth vector field y bar on that open set W. Okay, now you can use the theorem, which is a theorem I have mentioned. This is the theorem. If you have an X and a open set smooth vector field and open set U, then if you take any point P from U, then there exists an open interval I containing 0 and integral curve alpha such that this will happen. So since it is an integral curve, so by theorem what you can say, you can have an integral curve I from alpha from I to u here it is what w, correct? Your I to w such that alpha of 0 is equal to p, and it is an integral curve. If it is an integral curve, alpha dot of t must be equal to the vector field. What is the vector field here? Y bar of alpha of t for all t element of I, and alpha of t will come inside your w. Okay, now here f circle alpha whole dashed of t. What is this? Del f of alpha of t dot alpha dot of t. Okay, so this is equal to del f of alpha of t dot y dot alpha dot of t I can replace as y bar of alpha of t, correct? For all t element of I. So if t is element of I, alpha of t will come inside your W, correct? If alpha of t is in W, y bar and del f will be coming dot product. What comes? Dot product will come 0, correct? For all q element of W. So you can say that this is equal to 0. So derivative equal to 0 means f circle alpha of t is coming as constant. Okay, and it is coming as constant. Also f for f circle alpha of 0 equal to f of alpha of 0 equal to alpha of 0 we have taken as p, so this will come f of p, and f of p is definitely equal to your c. That is we have defined already in such a way that f of p is coming as your c. Okay, so you are getting your constant as c. That means this constant is going as c. Okay, so f circle alpha of t equal to c. So you can say here next, that is f of alpha of t equal to c for all t element of I. So the first part is proved, that is first two parts are proved, that is first is alpha of 0 equal to p, and what is the second part? Second part was coming as alpha dot of t equal to you are writing here as y bar, and y bar and x bar are same on your S. You can write x bar of alpha of t for for alpha of t element of S. Okay, and for t element of I, alpha of t element of s, if it is, then this will be equal. So that means alpha will act as integral curve for your x bar also. Now the third part, how it is proved from the theorem itself, you can say that by the theorem it says if any beta comes from I tilde to s such that beta of 0 equal to p, then beta of t must be equal to alpha of t for all t element of I tilde. This is true. This is true for what? This is true for all the t element of I tilde, and hence we can say that for whatever beta you take, if it you will get beta of t equal to alpha of t for this corresponding domain. That means all such beta comes as the restriction of this alpha, means alpha will come as the maximum integral curve. So this follows directly from the theorem. Third part directly coming from the theorem, no need to prove it again. So you can say by the theorem this will come in this way. That means alpha will come as the maximum integral curve. So only thing we have done here is we have defined an open set W and a vector field y bar on that open set, and using the previous theorem, we are applying the theorem on this W and y bar, and we are getting 1 and 3 directly. And since it is an integral curve, you can write in this way, and y bar and x bar is coinciding on S. That implies alpha will come as the integral curve for the tangent vector field as well. So the second part also proved from the, that's a theorem. Almost you might have followed little bit at least. This is direct application of the previous theorem. Only the construction part you have to see of the W and Y bar and apply the theorem to get all the result. Okay, read the theorem and write the theorem neatly with all the steps. That's all for today. Thank you.